So here we go on number 26. Sally's doctor is concerned that she may suffer from high blood pressure. A patient is classified as having high blood pressure if the pressure is above 140. Suppose Sally's measured blood pressure varies according to the normal distribution, with mu is 125 and sigma is 10. So that means from day to day or measurement to measurement, you don't get exactly the same number. You get a number whose mean is 125 and whose standard deviation is 10. A says, if a single measurement x is taken, find the probability that that value indicates Sally is diagnosed as having high blood pressure. That says a single measurement has to exceed 140. So to find the probability the value exceeds 140, we go ahead and compute z for 140 using the mean and standard deviation. So we're using x minus mu over sigma. We get a z value of 1.5. We go to the tables, we have the chance of being less than 1.5 as 9332, but we want to be above 140, so it's the opposite side of things. So you go 1 minus 9332 is 0.668. So even though her average blood pressure is good, about 6.5% of the time she'd be diagnosed as having high blood pressure. However, suppose we took an average on 4 separate days, and the mean result is compared with a 140. What is the probability that Sally is diagnosed as having high blood pressure? Well, now I compute a new z. It has to do with the mean of 4 values. The z for the mean looks like x minus mu sigma over root n. So there's the sigma over root n sitting there. N is 4. We averaged 4 values. So now that divides the standard deviation in half, and it doubles the value of z to 3. So 3 is way out here. The chance of being above 3 is pretty tiny. It's 1 minus 0.9987, or 0.0013. So those are pretty straightforward, but here's a harder question. Find L so that the probability the average exceeds L is only 0.05. So we know L is smaller than 140 because exceeding 40 happens very rarely. We want to exceed L and have it be 0.05. So we go to the tables and we want to find 0.05 up here as a tail probability. That shows at the bottom of the t-distribution chart if you want, or you can look in the body of the z-tables for 0.95 and you'll come up with 1.645. So that 1.645 corresponds to a tail probability or a p-value of 0.05 in the t-tables. And if you go to the body of the tables try to find 0.95, you can't quite find it exactly, but 1.645 is between the two values that cause almost 0.95 to happen in the tables. So you could use whatever value shows up in the tables, or you could use the one from the t-tables here. And then you're going to use mu plus z times the standard deviation, but it's x bar that we're finding, so its standard deviation is sigma over root n. So we do that, we take the mean 125, 1.645, 10 over root n, and get 133.23. And you can check to see if it works by putting it here into this formula and getting the corresponding z value that you need. On to 27. It says, 27 says, suppose 10% of new cars are subject to some kind of recall, and you sample 15 cars. So 10% of cars are recalled, and you sample 15 cars. In that case, the number recalled follows a binomial distribution with n is 15 and p equals 0.10. So that's if you sample completely randomly by simple random sampling. So the way we compute binomial probability, since we said it's binomial, is up here. The probability of binomial quantity is equal to a certain number is n choose k, or n NCR k on your calculator, p to the k 1 minus p to the n minus k. So if I find the probability x is 2, I'm going to get 15 NCR2. 15 is the number of trials. 2 is the number of successes. We think of sampling as a trial. Each sample we take is a trial. There's 15 in the sample, so 15 trials. We're going to compute this number by typing 15, going math, prob, NCR, hitting 2. and hitting enter, and that gives us 105. And next to that, I've got the success probability, which is 10%, so 0.10, raised to the power number of successes, which is 2. And I've got the failure probability, 1 minus 0.10, raised to the n minus k is 13. So I've got 0.1 squared, that's 0.01. I've got 0.9 to the 13th, that's 2542. I rounded slightly. And then we take out the product of those three quantities to get 2669. So about a 1/4 chance of getting exactly 2 cars that are recalled in a sample of size 15. And what's often asked is, what is the chance for B at least 1 is recalled? I'll write it like this: at least 1 is bigger than or equal to 1 for the number recalled. And since the number recalled could be 0, 1, 2, 3, and so on, to have at least 1 is the complementary event to having 0. And it's easier to compute the probability of 0 than to add up all those probabilities for 1, 2, 3, 4, 5, up to 15 possible recalled cars. So we go 1 minus the chance there are 0 recalled cars, because what's left is at least 1 recalled car. And then we say to ourselves, with no recalls, so all have to be not recalled. All 15 have to be not recalled. Each has probability 0.9. All 15 must be good. And we're saying that we're going to use the rule for independence. Use independence here, because sampling from a population, what you get on one sample doesn't impact what happens on the next sample. So this is an independent situation. So the chance is 0.9 for each, and there's 15 of them that all have to be the same way. So we do 0.9 to the 15th for the chance they're all good cars with no recalls. So we do 1 minus 0.9 to the 15th, and the chance there's at least 1 recall then is 1 minus the chance there's no recalls, which is 0.7941. That 0.9 to the 15th, you might be curious, I am. 0.9 to the 15th is 2059. Put it here. 0.2059. And this plus this comes out to be 1, I'm hoping. Looks like it does. Finally, in part C, it says find the mean and standard deviation of the total number of recalled cars. So we said the number recalled is binomial. So for binomial, mu and sigma, there's formulas for that, for binomial. Mu is n times p, n is the number of experiments, p is the success probability. In sampling, that's the number of items sampled. So 15 times 0.1, which is 1.5. And sigma is np, 1 minus p, p is 0.1, n is 15. We do that. Now, don't forget to take the square root here. I almost did. Lots of times people will do that. Okay, those are 2 rather involved questions, and these are the kinds of questions that people actually get wrong. So pay some attention, make sure you understand all the concepts on this slide, because they definitely are places where people lose points on tests, and it's worth spending the time to figure out how this works. Okay, onward we go.